Hi, I'm Marshall Ball. Today I'll be talking about some joint work with Oded Goldreich and Tal Malkin on communication complexity with defective randomness. I'm going to begin with a very brief review of classical communication complexity from the late 1970s as formalized by Yao. This will probably be familiar to almost all of you, but if not, I highly recommend looking into a number of excellent monographs on the topic. So what is communication complexity? It's formalized by Yao. Alice and Bob have inputs, each of length n, and they want to compute some function f on these inputs. So they run a protocol where they communicate and determine the value of f on x and y. And the question here in communication complexity is how much must they communicate in order to compute f? So an example of a function that we would be interested in computing is the equality function. So Alice and Bob want to determine if their two inputs are equal to one another. A simple protocol for doing this, a trivial protocol, is for Alice to simply send her input x. This works for any function. And Bob can simply respond with whether the two are equal or not. And Yao showed in his original paper that in fact that this is optimal. So far we've been discussing deterministic protocols, but one might ask, what if we consider randomized protocols? Does using randomness help Alice and Bob to compute f using less bits of communication? So here we're going to we want Alice and Bob to successfully compute on any input x and y with constant probability. So what do we mean by a randomized protocol? So there's multiple ways that you can think about this or formalize this different settings. So one is so-called private coin model. And here Alice and Bob each have the ability to toss unbiased coins privately. So Alice has access to her random bits and Bob has access to his random bits, but they can't, but they're hidden from one another. They run some protocol using these random bits to compute f. And in fact, these private coins, randomness can indeed help quite a bit. So for the case of equality, here on this slide is a protocol from Robin and Yao for computing equality that you can examine on your own time. But the important bit here is that if you allow private coins, you can save exponentially in the amount of communication. And another model, which is frequently considered in the literature, is so-called public coin. So here, Alice and Bob can see some bit string, unbiased, random, uniform bit string in the sky that's not counted towards their communication. So they see this random string and then they want to run some protocol given this randomness. Question is, does this help beyond the private setting? Indeed, at least for the case of equality, it helps even more. So you can just communicate, Alice and Bob can just communicate a constant number of bits in order to determine whether their two inputs are equal or not. So in conclusion, randomness can indeed help a lot. So right, for the specific case of equality, right, you have these exponential savings. Private coin setting and right, only constant number of bits are used in the public setting. So this concludes our review. I'm going to fast forward over 40 years to the present, and our question is, do defective random sources improve communication complexity? So all of these protocols and models that we saw before assumed that Alice and Bob had access to genuinely pure randomness. But what if we only promise that you have access to something that's unpredictable? For example, Alice and Bob can agree on what the headlines of the New York Times are, obviously this is not, genuine pure randomness, but it seems like there might be some entropy in this. Maybe they want to use this entropy to run a communication protocol. Or perhaps, they're both can see the sun and they're looking at sunspots, and there's some entropy in these sunspots, and they want to use this to try to save on communication. Or another example is sort of an analog of the private setting. These previous were like the public coin setting. So maybe like the private coin setting, Alice and Bob are, say, some low-end computing devices that are just doing some simple tricks based on heat or something like this to get things that are like a little bit random or entropic. Can they use this to save on communication? That's our question in this work. So let's formalize exactly what we mean by a defective random source. An L-bit source R has min entropy at least k if for every string W in the support of R, W occurs with probability at most 2 to the minus k. So this means that, right, the R is not too predictable. No outcome happens with probability greater than 2 to the minus k. So in particular, what we call, for sort of shorthand for this, we're going to call this an LK source. So L, right, is the bit length, and K is sort of a measure of the amount of entropy or min entropy of this randomness source. And this is a classic idea or concept from the extractor literature. So, like formally, our first model that we saw, public variant of public coins, we have the public LK source model. So here Alice and Bob have access to some LK source and they want to run a communication protocol. Again, just to remind you, right, what we're interested in is like how many bits do they need to communicate in order to compute F? That's the big question. And again, we have a variant of the private coin setting in this sort of degenerate sources or defective sources. So here, Alice and Bob each have access to independent LK sources, and they want to run a communication protocol. So what do we show in this work? First, we show some lower bounds. So bear with me, I'll explain what everything means later, but for now I'm just going to present things that hopefully will be clear to some of you at this point. But don't worry if these terms don't make sense, because I will explain them momentarily. So if we have a function f, right, again, on two n-bit inputs, it's a Boolean function, has what's called a fooling set of size 2 to the m, then both public and private LK source protocols for this function require at least effectively m, or whatever is the smaller of m, or L minus k. So m, right, is the log of this fooling set size, and this is a lower bound for deterministic protocols. So on the one hand, we have the lower bound is either whatever is needed for the deterministic protocol, for some functions at least. And on the other hand, or it's what's the deficiency of this randomness source. So L minus K is sort of like how many bits of entropy are missing from this source. So just to sort of look a little closer, let's return to our example from the beginning of the equality function. And let's consider, our models where L is equal to n and K equals to n over 2. So, right, we have a ton of entropy available to Alice and Bob in both the public and private settings. But what this lower bound says, because equality, in fact, admits a fooling set of size 2 to the n, this says that computing equality effectively requires, whatever the entropy deficiency of this thing is, which is linear in n. So, right, it's no better than the deterministic protocol you have all of this entropy available to Alice and Bob, but it doesn't help them at all. And in fact, what we show is that this lower bound for a large variety of L and K is in fact tight. So as promised, we have some upper bounds, and in fact, these aren't specific to equality, but are quite general. So for any function f, again, a Boolean function taking two n-bit inputs, and k, right, which is our min entropy bound, greater than 2 log n. So here we place some requirements on k. So in the public LK source model, the maximum number of bits that you'll need is L minus k plus 1, which is effectively the entropy deficiency of your source, times the public coin, here the public uniform coin, unbiased coin complexity of f. And in the private LK source model, the most bits that you will need is a term corresponding to the entropy deficiency, L minus k, plus a logarithmic factor, plus the private uniform coin complexity, communication complexity of f. Right. So just to reiterate, these bounds apply to arbitrary f. And now let's look a bit closer at these, how these results work. First, we'll look at the lower bounds. And before going into our actual result, we need to recall some preliminaries. So the first thing we need is this simple fact referred to as the coroners lemma. So here we can imagine writing our communication protocol as this matrix. So let's imagine a deterministic communication protocol between Alice and Bob. So Alice is going to correspond to the rows, Bob to the columns. And for each input x and y, we're in that corresponding entry in the matrix, we're just going to put the protocol, the transcript of their communication protocol, pi. The coroners lemma says that if this transcript occurs for some other inputs, x prime and y prime, then it actually has to occur for the Cartesian on like all elements of the Cartesian product of these inputs. So this is not too difficult to see as an exercise. This is the first fact we need. The second thing we need is this fooling set that I referred to in the theorem. So what is a fooling set? So a fooling set is a set of pairs of inputs such that for any sets x and y, such that the function f is constant on the Cartesian product of x and y, so all possible pairs in these sets. This fooling set intersects such this Cartesian product in at most one place. So let's look at an example of equality. So here, if we look at the sort of matrix representation of the equality function, so sort of like this transcript matrix from before, but here it's just for the function itself. Right on the diagonal where x and y are equal, we'll have 1, and everywhere else we're going to have 0. So here the diagonal is a fooling set. It's easy to see that any sort of any sort of rectangle, any sort of Cartesian product x and y, a set of inputs in this matrix, that where f is constant can intersect in at most one place. And so why is this useful? So imagine, red is going to correspond here. So Alice and Bob have some transcripts, sort of the output, the transcript corresponds to the color red, and suppose it occurs somewhere else, right? Because if the transcript is the same, the function obviously needs to be the same, so this needs to happen on the diagonal. Right, the coroners lemma says that means that it needs to happen here and here as well, which can't take place because right, the function is supposed to be 0 there, not 1. And so this means that right, from this we can infer that we need to color, or we need independent transcripts for everything in this fooling set. And right, this fooling set is corresponds to the number of Alice or Bob's inputs. So it's size 2 to the n. So it's, right, equality admits a fooling set of size 2 to the n. And any deterministic protocol consequently needs at least 2 to the n different transcripts, and so therefore you need to communicate at least n bits. So now I'll sketch how these ingredients yield a lower bound on the public source model. So the first thing we observe is, which I won't go into detail here, I encourage you to look at the paper, but it's a simple combinatorial consequence here. That we observe that if this lower bound is violated, then there exists some source R which has sufficient entropy, and 2 pairs of inputs in the fooling set, such that Alice and Bob, given this access to this random source R, always output this transcript pi on both pairs, right, with probability 1. So because S is a fooling set, F must differ on either X and Y prime or X prime and Y. Here we'll simply assume it differs on X and Y prime. And due to the coroners lemma, this gives us a contradiction, because we know that from the coroners lemma that they're Alice and Bob's, we can consider this for any fixed string R output of this source, we can consider their protocol as a deterministic protocol. The coroners lemma says that their transcript on X and Y prime will be the same as before. And therefore the function, what they get with probability 1 is the incorrect value of F. So this sort of completes the proof by contradiction for the public source model. For the private source model, I'm not going to go into the lower bound works similarly. The combinatorial claim requires an extra step, and I refer you to the paper. I want to turn now to how our upper bounds work. Again, we are going to need some preliminaries. We need to know about randomness extractors. So right, this randomness, the literature on randomness extractors is where this concept of this entropic source, this LK sources, comes from. And so what are randomness extractors? So a seeded randomness extractor, a seeded extractor, it's a function that takes as input a source, an L-bit source, and a short random seed of length d here, and output something. So x does a deterministic function. And the promise of a seeded extractor is that for any source with sufficient min entropy, if I give it this extractor, the source and random seed, its output should be close to uniform. So here u sub d or u sub m denotes the uniform distribution on d or m bits respectively. And a two-source extractor is again a deterministic function that takes, but here it takes as input 2 L-bit sources and outputs m bits. And right, a two-source extractor has the promise that for any independent LK sources, the output of the extractor is close to uniform. So in the extractor literature, your principal concern, right, is constructing these objects explicitly. Here, because we don't care about efficiency or anything, like computational efficiency at least, I should say, we don't care about explicitness. But the next fact we need is about randomness complexity. So this is from Newman in 91. He showed that in the public uniform coin setting, you need at most logarithmically many coins. And the same is true in the private coin setting. So you really don't need much randomness, only logarithmically many bits. So how do our upper bounds work? Let's look at the private setting first because it's sort of more intuitive. What we want to do is we want to use an extractor to convert our bad sources into pure coins and then run a very efficient private unbiased coin protocol. So how can we do this? Alice and Bob. Alice is going to cut off a part of her source that will contain sufficient entropy. So she slices off L minus K plus log n bits, sends it to Bob. Bob is going to use his own source to extract using a two-source extractor to get two sets of logarithmically many coins. And he's going to send one of these sets of coins to Alice. And now they can simply run the sum-efficient private coin protocol. It's clear where the communication complexity is coming from. And in the public setting, public source setting, we'd like to do something similar, but where we have just one source of randomness. So unlike the private coin setting where we can actually extract because we have independent sources, here we just have a single entropic source and there's no hope of getting purely random bits out of here. So instead we use a sort of idea from the de-randomization literature. So what are Alice and Bob going to do? They're going to fix some enumeration of seeds, all possible seeds, these short seeds for the extractor. And they're going to evaluate the extractor on their source. They can both see, and the seed to get, plausible public coin here. They're going to run their public coin protocol using this coin that now both of them know without having to communicate. They need to communicate for the protocol, but not to know the coin. And then they're going to do this for all possible seeds. Having done this, they're simply going to take the majority. And the promise is, because the extractor is close to uniform on a random seed for this source, the protocol, the public coin protocol itself is good. This works. So it's easy again to see where the communication complexity is coming from. So to review our results, the communication complexity of f for k that is super logarithmic, and f such that 2 to the m is a lower bound on the fooling set size of f. In the public LK source model, we have an upper bound of the randomness deficiency times the public coin communication complexity, and a lower bound of the minimum of m, which is this fooling set bound, lower bound on the deterministic protocol for f, and the randomness deficiency, L minus k. And again, in the private model, we have an upper bound. It's randomness deficiency plus the private coin communication complexity plus a logarithmic factor, and a lower bound, which is the minimum of, again, this logarithmic of the Fooling set size, or L minus k, the randomness deficiency of the source. So there's a lot of work left to be done here. So one problem is there's a gap between our bounds. So right, in the public model, if right, we considered as an example this case of the equality function. So here the equality function admits a public coin protocol that's only a constant number of bits, but in general, public coin complexity could be higher. And here, if this is the case, then there will be a gap between our upper and lower bounds, even if the problem admits a good Fooling set bound. And this brings me to our second open problem. Can we prove more general lower bounds? So, right, equality admits a very good Fooling set bound, but in general, Fooling set bounds are not ideal. They may be exponentially far from the deterministic communication complexity of the function. So, like, this is the case for inner product. What we would like, I mean, sort of what our work suggests might be true is that there's a lower bound of, following form. The minimum of, like, either you use the deterministic, you have to communicate according to the deterministic communication complexity, or L minus k, the randomness deficiency of your source, whatever is less. But we don't know how to show this. Another question is, what about the case of very small min entropy? Our upper bounds are relying on these randomness sufficient variants of public and private unbiased coin protocols. But these protocols still require logarithmically many bits. If you have less min entropy, then you're going to have to do something else. Both of our models admit very poor communication protocols, at least for certain functions. In many settings where Alice and Bob, in fact, have access to a lot of entropy. And this might lead one to consider perhaps a hybrid of the two models, where Alice and Bob have private sources, their own private sources, and access to a shared source, in which case they can indeed extract and do something communication efficient. Thank you for listening.